Emotional, mental, spiritual, and physical. So wait, Mr. White's pulling it. No, pull it. You also stood up. Without constant, the class is much. Yeah, well, he's stood up. He's bullied. Yeah, no, it's not bullying. I was sitting down and you stood up. And mine was down there. Wait, Ollie, you can print your lunch to give it to lunch. Yeah. Oh, yeah. Are we allowed? Yes, we are. Monday, Tuesday, okay. I will.
That's what I'm
I know, right? Well, actually, yeah. I don't I dare you to drop it. Yeah, one of the questions I added Justin's back. That's fine.
Okay, so grab a seat, let's go ahead and begin. And let's see if I got some folks here. I do. I got some online people. Hello, online people. So as I mentioned, we're going to do my folks online and you here at the same time. And that is good. So I'm going to write down my folks that are online. From your group, anybody missing from your folks that are here?
Not that
You look complete. You look complete.
Is George after our group? Yeah. George is around. I think so. George. He's down here. I forgot that George was in our class. Yeah.
He's not in this section. I've never seen him. Okay. Okay, so I got Lisa. Hello, Lisa. I'm writing us down here. Hello, Yo. I've got Stephanie and Aaron. Stephanie and Aaron. Hold on just a moment. I'll get it from you just a moment. And I got Frederica. Anybody else say hi? Jordan would be in group B, but he never came. Thank you very much, Lisa. Okay, Brooks, thank you very much. Any other of the parental consent forms? If you already submitted on Google Classroom, I don't need it. Hands down. If you did not submit it on Google Classroom, then do so or bring it to me. Okay? All right. And I might have lost my folks at home. Let's see if they're still there.
Wait, Mr. White, I thought you needed all the permissions before you can actually stream.
I am taking into account that I did my own permission slip at the start of the year, if you remember that. So yeah, I think we're more or less covered, but I'm doing this one to make the administration happy as well. But we handed in the other one already at the start of the year. But now we got two because they want another one. Anyway, thank you, Brooks. Okay, folks at home, if you have not done so, please take a picture of your filled out parental consent form and upload it to Google Classroom, so I have that as well from you. Thank you ahead of time for doing this. Good. For both groups. I can see this isn't gonna work. I wanna move a couple of you up. So, come on up here, Nick. And you don't need to be back there as well, so come on up, Marino, and be here as well, because I'd rather have you up front. There's no reason to be in back. And let's do the same with Jonathan. Jonathan, come on up. Be here as well. That makes the most sense. I don't need a bunch of empty seats. And I got a Keanu, good. Let me write you down, Keanu. Super, so I can give everybody points who showed up here. Anybody else? I got 1, 2, 3, 4, 5, 6. If there's a 7th person, looks like there is, please say hi. I got Lisa, Yo, Stephanie, Aaron, Federica, and Keanu. Okay. We're starting something new, and it's a bit about this. Collision theory. See if folks at home can see that as well. So what do I mean about collision theory? You and I are going to use, especially, hold on a second, you're going to use the idea of gas particles, like in the air. So we're not going to worry about solids or liquids for this, to keep it simple.
I have a question. When are we going to get the quizzes down here on direct?
Probably right now. I graded everything, so let's see where they are. You mean the quizzes we took, right?
Yeah.
Yeah.
Well, you could either get one or
The folder is on my desk. Let me go get it.
no, because when sometimes it's about from the version, you get the wrong answer. Something else is like how you can wrong and how it ended up. Oh no. I got the right answer, but I know I don't celebrate it. I kind of got everything wrong, but I was and I'm just right now.
Boom.
Wow. I just closed the door. Yeah, I know. I was not I was there on Mother's Day.
Make it better.
This one goes, fine. Here, go out here. Hello, people from the live stream. Hello, YouTube. Hello, YouTube. Hey, YouTube, don't forget to like and subscribe. Oh, yeah, they can hear. And also, put on the post notifications. So you get notified. Get that like button. Like notifications. It's only, it just hasn't printed paper either, so I can't.
Me neither.
I'll have to print it once, but.
All the one. Not me neither.
Yeah, no, 'cause I already have my freaking printed then.
I'll do yours, Chelsea can do mine, and then.
What about me?
Oh my god.
No,
You
you-
find someone else. There's one video. We're the three.
Sure.
Whoa. There's three people like that. So.
Wait, send it back, right?
Yeah.
Okay, perfect.
Wait,
But
but
I
I
you
got-
haven't gotten the
And
notes
those
back
are
to
the-
us.
there we go.
My first one's on.
Where is
Okay, He's in another camera.
Wait, you had work?
No, no.
You can't go all the way to the
My
top.
first step is like that.
Yeah, really good.
I hope you don't run it all.
No, I mean, that's just after the third section.
I thought that would be so cool.
Okay, there we go. Anybody else there? All right, and Aaron is there. Oh, got Aaron already. Good. So quiz is coming back. Sorry. Yes. Kelly. You see that? I know. Good. Okay, now we can actually start up, and everybody out there said hello, who's one of my students, hopefully, okay. Collision two. Let's begin. Julius? So, in the air, I got lots and lots and lots and lots of gas particles. Right at the beginning of this year, you and I acted that out, and I had you move around and so on to imagine that a little bit better. Now I want you to imagine that they're hitting all the time. So every particle is moving so fast, they're colliding millions and millions and millions of times. So gas particles collide millions of times. Mostly, nothing happens. How many of you have been on like a ride at a amusement park where they call it like bumper cars? And you sit in and you bump into others? Okay, so Nick, what happens when you bump into other cars with those?
Both you and the other person bump back.
Does it destroy the little car?
No.
No. The little car's okay, isn't it? Because you got a little bumper, okay? If you haven't done that, how many of you have played pool or billiards? Okay, so pool or billiard table?
Like, no, I'm talking, how did you not play pool before?
Pool.
Okay.
Like
Billiards, pool. Okay, everybody's done that. Good. So when I hit the cue ball at the other balls, there are lots of collisions, right? Do I destroy the other balls when I hit them with the cue ball? No, Taylor Court, not right? They're fine. Gas particles are really similar. Okay? So think bumper cars or billiard balls. Or just some billiards, I could say. Okay? But what chemistry is really about, oh, I got a new person. I got Emil has joined us. Good, Emil, thank you for checking in. What chemistry is really about is called effective collisions. Effective collisions, what does it mean when something's effective? What do you suppose I mean by that? Brooks?
It works.
It works. Something, if it's effective, it works. And how would a collision work? Remy, what might that do?
Well, effective doesn't really mean, it means it has an effect on something, it doesn't necessarily mean that it works.
No, it can mean it works in this case too. The effect that we're talking about, so what I mean by effective collision is hard enough to produce a reaction. So effective means it has a good effect if we want the reaction, so to speak. It's effective to go ahead and do something. So before we continue, here's my trick about chemistry. Ready? Here's the short version of what chemistry is. Chemistry is this phrase, break bonds, then make bonds. That, my friends, is 90% of chemistry. We're going to see what I mean by that. I'm going to do an example right now with you that we essentially already did once in this class, but our example is going to be making water vapor. Okay, I want to do it in words first, okay? We did this as a test, I think, for one chemical anyway, for one gas. And we said part of the test is these two elements get together and they form water. So my question to you is, what gases are we starting with that go on and make water? One of them must be gas, and the other one must be gas. Give me one, Marino.
Oxygen.
Oxygen. So I got oxygen gas plus, all right, what must be the other gas that's in water? You see a hydrogen gas. Forms water. Now we're going to do it in symbols.
Is so hydrogen effectively oxidized, is water effectively oxidized hydrogen?
Yes. Along with the oxygen glued onto it. Okay, so a lot of what I'm going to do now, you're going to have again next year, so don't panic. Ooh, it looks like I got a comment here. Yeah, some of my folks at home had that as well. Good. Oxygen and hydrogen gas, Stephanie and Lisa both had that. Oh, and you're a bit late, Coco. I'll mark you down, but you may want to. Actually, as long as you write down what's on the board, Coco, you're okay, because I had to go get something in the classroom. So anyway, so just write down what you got here. Oops. I hope I'm still there. They just gave me to another website. Okay, hopefully I'm still there. Okay, they still. So here we go. Here's oxygen. Oxygen, and you probably know it's O2, right? O2, you've probably heard of that. I'm breathing O2 because they go on in little pairs. Turns out they got a double bond in between them. They're bound pretty tight, like that. And they're diatomic, right? Good word. So, and another one that's diatomic is hydrogen. I'm going to write that as H's. Now look back at what I wrote in my chemistry means to break bonds, then make bonds. Okay, folks, I want to make water. Give me Give me, Tully, give me the formula for water. H2O. I got two H's and one O. Can you guess for an H2O who's in the middle? Who's in the middle of the molecule? Julius. H. Second guess?
O.
Yeah, it's got to be O because I got one O and two H's. So it's going to look like this. Again, you'll learn some of this next year. It's not a big deal. But here is what is important. Folks, what do I got to do with the O2 before I can make waters? What do I got to do with this sucker? Julius? Exactly. What do I got to do, Julius, with the H2? Break bonds, then we got to make bonds. Okay. Now, I haven't balanced this at all. If this doesn't look right to you, it's because we're not done yet. But maybe somebody can help me balance it too. Like, I need to have the same amount of H's and O's on each side, so I got to have like some multiple. Brooks, you want to help me out?
Wouldn't it be like the diatomic rate would be one of the two?
It would, but like I can't have, I could do that. You mean take half of an O2?
Yeah.
I could do that. But for this one, I want to make it look a little cleaner. Let's double it instead, Brooks. Could you double the numbers? And how many would I need of what?
44.
Yeah, I need 4 of what?
Hydrogen.
Yeah. So here's how I'm going to do that. So I'm going to get 2 molecules, okay? There's an H and H, and there's an H and H. I'm going to put a plus in between them here. You'll see where we're going, everybody. Just keep your arms loose. We're going to be good. Now, how many waters could I make? I only got 1 here, but now I got enough reactants to make what? You see that? 2. So I'm going to make my second one and just put it over here. Okay, but here's why I did this. Let's go back to the comment. Was it Brooks or Julius? It's Julius. So let's go back to the comment of Julius. And let's put arrows here and say, hey, first, we need to break these bonds. That's super important. It's a big part of chemistry. Because a lot of times, let's say here's my H2s and O2s. A lot of times they do this. Boop, boop, boop. They don't hit hard enough to react, to break up, right? Yeah. They gotta hit hard. If we hit hard, we get what's called effective collisions. And we can break them up and then maybe make something new. So not every time molecules bump, just like billiard table balls or just like bumper cars, not every time it's not going to do anything. Many collisions do nothing. What we're going to talk about the rest of this hour, and probably next time too, is what if I want a reaction to happen? What do I do? And we're going to answer that in an interesting way. But first off, let's kind of recap. So okay. We must break up reactants before the atoms can be into molecules. Okay, this is a bit of review, but it's essential to know these terms. Which side, how about Jonathan? Which side was the reactants here and which side is the product on the arrow?
The product is H2O.
Okay, good. So the right side's always the product. And the left side is the
Yeah.
reactant. In this case, reactants. There's two of them, right? So it doesn't matter how many reactions you write, the left side's always called the reactants. Okay? So, just like if you were building something when you were really young, you want to build something new, first you got to do what with the old one. Yeah, you got to
Break it apart.
break it apart before I can build then something new. It's the same thing here. So what's a good word I could put? We must break the reactants before the atoms can be into products.
Rebuild.
I like that. There's another word I was thinking of too. It starts with an A. Re what? It starts with an A. Can you guess another word?
Reassemble.
See, Tilly. Tilly. You're not Tilly. You're not Tilly. With an A. It means to move something around. Not remove. Rearrange. Thank you. This year. So rebuild, yes, Nick, or rearrange. Yeah. And that's really the best way to think of chemistry. If you can think of that now, you're going to be set for ninth grade, because a lot of ninth grade is studying the mixing and rearranging. That's a lot of what ninth grade chemistry is. And I'm ignoring my people at home. Sorry, people at home. In fact, they can't even see all this. I'm so sorry. Look at that. I don't have this very well. My cord doesn't go very this far. Okay, so my people at home, my apologies. Let me read this off, and then we'll continue everybody together. So the top word says, okay, we must break reactants before the atoms can be rebuilt or rearranged into products. And then, how to make more effective collisions. All right, let's see if there's any other comments, other than the fact that you couldn't see any of that. I'm sorry about that. Okay. Making water vapor. I'm sorry, Stephanie, I don't know what you're referring to. Let me read some more. Yeah, okay. Okay, Lisa says, can I reread the thing again? Okay, here's the, I won't use that marker anymore though. Not today. The says, chemistry is break bonds, then make bonds. That's the, everybody at home. That's hard to read. Chemistry is break bonds, then make bonds. That's the guts of chemistry. Okay, how to make more effective collisions. We're going to talk about a parking lot analogy. An analogy is like a story. It's sort of like something else. A big comparison, like a big scale comparison. I mean, right. So here's the analogy. Okay, how many of you have either seen or been to like an American store with a really big parking lot? We're interested in the parking lots. They're really big there. Okay, so I want you to imagine now a special parking lot, folks at home too. a really big parking lot. Around the edge of the parking lot, you've got like rubber bumpers, just like on a bumper car at the fair. And inside the parking lot, you've got 10 people driving cars. And the 10 people are driving always 30 kilometers per hour. Okay, then, here's the last thing. The 10 drivers, they're blindfolded. This could be bad. What's going to happen? We set them loose. Ready? Go. What's going to happen? You see that? Nothing? They're going to collide. Are they going to start to dent up their cars? Yeah. So we're going to start getting some collisions. Okay, so really, can you see them? Let's say when they hit the sides, they bounce back. Pretend they bounce back from the walls. Now they're hitting more. They're colliding more. Okay, that's what we got. Let's say when they collide, and like I get dents in their cars and stuff, that's an effective collision. Okay, that's going to be defined as an effective collision. Okay. We'll pretend that people don't get hurt, okay? We wouldn't really do this, obviously. Okay, now. I got a request to read this again because I can't get the quote over it further. Okay, we must break reactants before the atoms can be rebuilt or rearranged into products. How to make more effective collisions. So the parking lot analogy. So here's my question to you. Give me one way that I can make even more collisions. What could I change about this weird situation? All right, Nick starts off.
You have the driver to drive faster.
You got it. So one way is I could increase let's say instead of going 30, now we're going to have them go to 100 kilometers per hour. So for more collisions, increase their speed. Whoa, what a mess that would be. So from 30 to 100. Oh, man. Oh, ouch. So they could drive faster. How else could you change the situation? Give me another thing you could change about the situation. All right? Ready? I could do that. I could make the area smaller, but I want to put that on hold. We'll come back to that, Remy, but not just yet. Give me another idea, Kelly. Add more cars. So we had let's say we had 10 cars in there. Now we're going to add another 40. So let's say now we got 50 cars in the parking lot, all going 100 kilometers per hour. Oh, 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 oh. Man, are we getting collisions now? It's really ugly out there. Now, in a sense, adding more cars is kind of like Remy doing what that you said. Make it so if I make the area smaller, in a sense, it also does a similar thing.
You could make the cars bigger.
I could. Okay, now that's where the analogy doesn't work with gases. Here's why. In gases, compared to each other, they're so stinking small that the size really doesn't matter much. And they're so far apart that it doesn't matter. So ironically, even though in real life the size of the car would matter, it doesn't really matter much in terms of gas particles. But adding more definitely matters. Now, good. Well, that's the one I don't want to use. Let's talk about chemical reactions. What you and I haven't talked about yet is they have speeds. They have speeds. They can go at a certain rate. speeds of reaction. And quite frankly, the more collisions, the faster they go. And now here's where we're going. Let's see if folks at home are still with me. Yeah, the time is still reading. So chemical reactions, it has to do with speeds of reaction. And the more collisions, the faster they go. So now, come from the idea of the parking lot to the idea of like particles. What would these be like? What could I do if I want a reaction to react more? What could I do with the chemicals instead of the cars if I want more collisions? What could I change? Start us off, Jonathan.
Make them warmer.
Make them warmer. What would that be like up here? Can you guess? Yeah. So if I make them warmer, we could say we're turning up the what, folks? Brooks?
Like the engine or the gas?
Yeah, but we're turning up what thing?
Engine.
Yeah, we're turning up the what to make it warmer. I'm not looking for a hard word. How does it get warmer outside? It's a higher what? Temperature. So another way to say to heat them up, Jonathan, is increase the temperature. It turns out that helps in two different ways. I'm going to put an A and a B here. So now, imagine I increase the temperature. So now the particles are going faster, just like the cars were. Why does that make collisions more effective? Why does it change things? There's two reasons here. Want to give me one, Maddie?
Because of the law of conservation, that energy can't just randomly disappear, it has to be transferred. Therefore, the atoms are going to absorb the energy and therefore become faster.
Yeah, and you're right, but that doesn't answer my question. My question's a little different. Let's say they're moving faster already. How does that change the type of the collisions? What happens? Because they're moving faster, what happens, Julius?
The collisions are harder.
Yes, stop right there. Good. So if I'm moving and two things hit at 100 kilometers per hour, bam! That's going to probably result in a lot more things breaking up. I know I'm pointing at real atoms, but you get my idea. So if they hit harder, the collisions, like Julius said, are more forceful. And let's underline forceful. Did you have forces this year in physics? Kraft?
Yeah, we did.
We did.
I think you did, didn't you? You should have.
Yeah.
It's the same thing. Force, a push or a pull, in this case, a really big push. Boom.
Oh, we did like two worksheets on this.
There you go. So you talked about forces. Okay, collisions are more forceful and often successful. Good. And then there's a second aspect. Yeah, exactly. So collisions are worse, but we're going to say, Lisa, that it's not a bad thing if we're not talking about cars. Now we're going to talk, Lisa, about chemicals. So we're just going to say that they're going to be hard enough to break them up, which is sometimes what we want to do. So collisions are more forceful and often successful. And if they're going faster, something else happens too with the collisions. Something else happens. Brooks? What?
Stronger?
No, that's the same thing. Forceful is the same word as stronger. That's not any different. Now, what else? If they're going faster, then something else changes too. You see?
More fluid.
Exactly. Yeah. So, like UCN's just figured out, those two effects make raising the temperature really effective. Even a little bit matters a lot when we raise the temperature in chemistry. We're going to come back to that in a second because I want to get to the other thing before we run out of time. What about adding more cars? What could that be like for chemistry? What could adding more cars be like? What do you know?
Adding more reactants.
Yeah. Add more reactants. Another way to say it, because a lot of the stuff you're going to do next year is about concentrations of solutions. You can also call this increase the concentration.
Is that why scuba tanks are really volatile because they're so compressed?
Yes. And the concentration is kind of also what Remy alluded to earlier when Remy said to make the parking lot smaller. Well, that also makes the cars more concentrated, if you know what I mean. So if they have less space, then they hit each other more. Or if I just add more of them, they also hit more because there's more in the way. Brooks.
What's density?
It's essentially the way you're saying concentration is like density.
Dying, it's similar. It's similar. Well, actually, you have moles, so let me tell you moles. Okay, so let's say I have a solution of salt water. You know what I mean, Brooks?
Yeah.
So let's say I put 1 mole of salt in a liter. Ready? Boom, stir it up. Okay. So now the little ions are floating around in the water, right? Na plus and Cl minus floating in the water. If I want to make more concentrated, can I add another mole of salt? Stir it up? Sure, right? And that's what I mean. So often it doesn't look like I'm squishing it, but if I add more and more salt, I get more and more ions in the liter of solution. So that's what I mean, Brooks, about more concentrated. And I realize there I'm talking about a solution. Up here, I'm mainly talking about gases. I talk about gases because it tends to be a little easier, but to be honest, 9th grade, you're going to deal a lot with solutions. So why I told you about Brooks, that as well. Okay. Other questions, comments from you so far? There's a third way we're going to talk about too, but we're probably not going to get to that today. So instead, let's go back and give you an idea of this one, increasing the temperature. That's pretty cool. Is there an eraser in here? That's my eraser? Oh, that's pretty disgusting. There's no other one? Well, that's a fun hard to do. How about that? It's not much of an eraser. Huh. Okay. Somebody walked off with it. It wasn't me this time.
Yeah.
Yeah? You better get him next time and tell him to return his stashed eraser. Or whoever it was. Okay. Sometimes, we got a minute anyway, I'm not gonna write this. Sometimes, folks, when you get sick, you get a fever. What happens when you get a fever? What happens to your body?
Your body heat increases.
Yeah, well, the what goes up?
The warmth. No,
No, come on, we use the same word over here.
the temperature.
Temperature, thank you. Your temperature goes up. Now, can you guess why? Now that we talked about this today, why does your body do this? It does it on purpose. Why might your body be doing this?
Well, I know to heat up the bacteria, make it move faster, burn it kind of.
It's not to make the bacteria go faster, but they do. It's to make something else happen. Ready?
So that's the virus or whatever our immune system gets full.
Yes, but how? What does it make move faster? Not the virus. I don't care about the virus. It makes the defenses. All your defenses move faster and kill the virus quicker. So that's sometimes we want the reaction to happen fast if it helps us. So your body turns up your temperature. Good. Thank you. What does number 2 say? Number 2 says add more reactants. Add more reactants, increase the concentration. Thanks everybody for joining me. We'll see all of you live next week. Bye. Okay.